Okay, so on our last presentation should be given by Lakshmi, Professor Lakshmi, right?
Papers, several literature, and we found that this comparison of aerosol optical depth, especially obtained from the global climate models of coupled model intercomparison project 6, they were mostly confined to a regional scale actually. So people try to compare this aerosol optical depth with the satellite products. I think satellite AOD derived from MODIS and other things. So we thought that, and we thought searching, how this globally, they are matching, what are the discrepancies and uncertainties in the model data products. And sometimes that there are some discrepancies in satellite data products also we come across. So whenever we compare satellite data products with the in situ measurements, and always we found that in situ measurements have been taken as the reference, and we try to compare this satellite data whether they are providing the exact values or not. So here this is a little different thing is that we try to compare the model simulations. Since we have we have planned to do it this globally, so we don't have any reference data sets except the satellites. Other than we have some like observations like aeronet observations we have over the globe, but the you can say that the coverage of aeronet stations is very less. So the comparison of this global scale aerosol optical depth products from the models is will not be a fruitful outcome. So that's why we thought to compare this global climate models aerosol optical depth with the satellite products. So here we have considered the satellites MODIS, MISR, and ATSR-SU. These three satellite products we have used, and the result of this work has been published in two journals. So one was in the International Journal of Climatology, and other one is Environmental Science and Pollution Research. So I will be presenting some of the results that have been published in these two journals. So I'm just going directly to the main work because of lack of time, and I have not prepared it very detailed wise. So, and also I'm sure that people are presenting in the audience are having some good knowledge on aerosols and air pollution. So I can skip some of the basic formulas so that I can deliver on the results. I can spend more time on the results. So the main objectives of this work is, as I mentioned, that aerosol optical depth trends, and we have taken multimodal mean here. So multimodal mean means we have selected, I will show you the later slides. So we have taken 26 global climate models, and then we have averaged them, the arithmetic average of these global climate models. And then that each global climate model we have considered the single realization. So we know for every global climate model there are different realizations. You can see with different initial conditions you have different realizations. But actually for this study up to a certain point, since we have a good number of global climate models, so we have taken the single realization and we have averaged them, that we call it as the multimodal mean or triple M of GCMs over different hemispheres. So how globally and hemispheric wise how these trends are changing, and of course the mean annual AOD also we have seen. And then the second part will dwells on comparison of AOD with MODIS and MISR products. Here actually the thing is, here we have done little extra when compared to the existing literature. So we did compare not only the aerosol optical depth, but also we have used different wavelengths from the model as well as the MODIS and MISR. And then we have derived the angstrom experiment, and then these angstrom experiments also we have compared, and we try to explain these changes with respect to the seasonal cycles of the like say we can say aerosol optical depth. So the third part deals on we have focused to India actually, how this AOD trends with respect to the MODIS, and also we could compare this over India, how this the earlier version of CMIP, that is CMIP5, which was released in 2013 or 14, how they are comparable to CMIP6, which was released around 2020. So these three actually I will be presenting. And of course, these are the different models which we have considered for our study. There are almost 26 climate models we have seen. And you can see the right-hand side, the availability of AOD data. So there are three wavelengths, basically 540, 440 nanometers, and 870 nanometers. So when we see that, in 550 nanometers, like, in the visible range, actually, you have, sorry, in 550 nanometers, you have most of the models have this AOD data. When it comes to this 440 and 870 nanometers, we have very, very less number of models available. So this makes that, when studies, just like that, we want to see the trends, we have considered only 550 and 550 nanometers. But of course, if you want to estimate the angstrom exponent, so we have to be more selective among these models also, where you have at least 2 wavelengths for angstrom exponent, and we also derived the first derivative of the angstrom exponent, which needs actually 3 wavelengths actually. So like this, we have selected a few models only among these. And when we see these 26 global climate models, again, what we have done is initially on larger scale. So we have compared with the global MODIS and global MISR products. So these figures show the Taylor diagrams of modeled AOD for the 26 models, and the MISR and MODIS AOD. So here, what we understand is when we see these 26 models, they are having different trends. Like, when you see exactly, some trends are not significant, some trends are declining trends, some trends are increasing trends. So to bring it to the uniformity, we have compared this each model with the multi-model mean, and then in addition to that, we also compared with the modeled satellite AOD also. So in that way, we have finalized mostly. I think we have come across most 8 models of the AOD, which has good of 26 models, and also the global MODIS and MISR products. So we have averaged these 8 models, and then with that triple M, that is multi-model mean, we have proceeded for the study. So these heat maps show the mean annual AOD as well as the trends of the AOD for different hemispheric regions. Like, we have done globally. At the bottom, you can see the global AOD, how it is changing. Then you can see southern hemisphere, northern hemisphere, southern polar and southern mid latitudes and southern tropics, northern tropics, northern mid latitudes, northern polar region we have done. And this we have done separately when it comes to the land, how it is changing, when it comes to the ocean, how they are changing, or when it is when you have the combined product, how they are changing. So mostly we found that this is especially the northern tropics are having the increasing trend. When you see at the right hand side figure, wherever the dots are mentioned, you can see they are the statistically significant trends. So single dot represents the 0.011 level of significance, and double dot represents the 0.05 level of significance. So in this way, we understood that when you see any of the case, like when you take the combined data sets, or when you take combined ocean data sets, or when you take the land only to the land, there is no significant trend of AOD we have. Rather, when you see globally, the trends almost the declining. So declining means they are not significant, but you can see the tendency of the AOD is declining globally. And then we just compared with the you can see that mean annual trend of this is done spatially we have done. So when you see the spatially, you can see that the AOD, that is, one is mean annual AOD, and second one is bottom figure represents the trends of the AOD. You can see the bottom line is very interesting. You can see some regions like India and Eastern China. So though they have higher AOD, they are also significantly increasing. And whereas when you see in big latitudinal regions especially, they have the decreasing trend of AOD, but even then they are very significant. This shows that some various policies. Yes, sir. Yes, I'm just running through. And this is in comparison with Modi's and this is the absolute. You can see that, sir. This 5 minutes is for this presentation or our next talk also.
Total.
Oh, okay. And this is the absolute by us we have done. Actually, the schedule it was mentioned half an hour for both of the talks, so I prepared in that way. And I will cut short. Okay. And this is the absolute bias. Then actually, as I mentioned, we have taken only we got only 2 models which are having the dual wavelength or triple wavelength. So that is why we have calculated. That's how we calculated the angstrom exponent. You can see the formula for angstrom exponent is given in the equation 1. The first derivative of angstrom exponent is given in the equation number 2. And we find that 2 models, how they are changing. When you see, especially when you focus to the Indian monsoon region. So when you take in the July, the angstrom exponent shows the lesser values, which obviously says that the dominance of the large-scale particles, which is meaningful because in the Indian monsoon region, in the July time, you have the southwest monsoon currents, which brings the natural aerosol. They are mostly the coarse mode aerosols. So in that way, we confined our studies that models are able to capture the patterns of the AOD, but not exactly. This is interesting thing when we compare Modi's angstrom exponent with respect to the ATSR SU. There's a lot of discrepancy. You can see that in especially some areas like Australia and North Africa, these things, we have higher value of the uncertainty we can see. And when it comes to the India, this is how they look like in CMIP5 model mean as well as the CMIP6 model mean. There's a lot of discrepancy, whereas in CMIP5 they are underestimated, whereas in CMIP6 they are overestimated. And then we have compared this how in future levels, when you take the shared socioeconomic pathways of AOD, how they are being contributed, you can see for different things. You can see anthropogenic aerosols, BC, dust, they are all contributing to the AOD, future AOD over India. So with this, I thank you very much for this talk. Now let me open the second talk. I hope at least I request organizers to give at least another 5 minutes, so I will finish the talk also.
Yeah, please.
Yeah, I'm just sorry. I'm just running.
Sorry for any confusion, but we are behind the schedule actually.
yeah. And just actually,
Please.
Hope you are seeing my screen. Actually, this is the earlier presentation which I made is actually global scale studies we have done. Actually, this work I am presenting, which I have done at my previous institute. Actually, we had a regular measurements of black carbon as well as the aerosol optical depth, for 10 years, like 2010 to almost 2020 we have. So with that, what are the different studies we have done? I think I'm just trying to present here. So this is the site location, which is located in the east coast of India. This is called Chennai. And this is the site description. I'm not going through this. And earlier we have done recently long-range transport of aerosols we have studied. And of course, we have separated the scattering and absorption component coefficient from the aerosol optical depth. And we also studied the estimation of aerosol radiative forcing and its comparison of surface solar fluxes. And then we also have carried out the source apportionment of black carbon aerosols and chemical characterization of surface PM10 also we have done. So now I will be presenting different instrument that we have used for our study. We have used the atherometer and we have used the microtop sun photometer. We have used mini micro pulse lidar, which gives the through which we measured the boundary layer height. And then we have used the laser precipitation, that is dysdrometer, to study the raindrop distribution impact on the aerosols. And of course, we have always used this automatic weather station. And these are the details about the instrument, which I am not showing now. And this is, of course, the picture for the details for the mini micropulse lidar. We have this data from 2016 to 2019, 2020. We have this. We have used to study the fumigation of the aerosols. Actually, so when you see in the morning, especially after the sunrise, there is a peak in the BC diurnal variation. That peak in the diurnal variation of BC is mainly because of the the aerosols which are present in the reduced boundary layer, they get disturbed. So because of that, there will be high concentrations of BC or aerosols. That peak refer to the fumigation effect. So, and this is you can see that here you will understand exactly the peak is in the morning time, especially after sunrise. You will see the main intention is that when you have the peak BC and then when you have the sunrise, there is a time for almost half an hour to 1 hour based on the seasons, basically. When sunrise
Can
begins
you
first.
put this presentation mode? Big size.
Yeah, sure. Yes, sir. So this, I think this is, I think very, very very known figure actually. You get the morning peaks of BC just because after the sunrise effect. Because just after the sunrise there is a gap and it will take certain time because of the temperature inversion takes place, and due to that there will be peak in the BC. So this peak in the BC just after the sunrise is referred to basically the fumigation effect, and this we try to see based on the collocated measurements of the black carbon aerosols and also the atmospheric boundary layer, which is obtained from the, you can see that
it is not in presentation mode. Some people are writing. Can you
it is in presentation mode. I think it will come. Yeah, maybe net is very slow. And then this shows the source apportionment of black carbon. The source apportionment of BC by wavelength exponent, and we have used this formula to understand what is the source of BC basically. So the source of BC generally based on the angstrom exponent calculated from the BC. BC we have, when you have ethalometer, we have 8 wavelengths, it will provide the carbonaceous aerosols. Then there is some segregation that if the wavelength exponent is more than 2, it is from the biomass burning, and if it is less than or equal to 1, it comes from the fossil fuel burning. So over our study region, we found that most of the days they are from the BC. The source of BC is from the fossil fuel burning. And of course, this is the long range trajectory. Already some people have presented on this the aerosols for the different seasons. I'm not talking much about it. And this is how because being a coastal station of our study region or Chennai, we took the advantage what will be the impact of the sea breeze effect on the aerosols. And we identified the sea breeze onset timing. So we found that sea breeze onset is happening different things, but mostly the sea breeze is most of this is in between 10 to 12 hours. And we studied this, how this sea breeze effect suppressing the BC, because sea breeze comes from the natural aerosols, whereas BC is you can see that, it's anthropogenic aerosols. When aerosols from coast region, which are aerosols, when they come here, they suppress the local BC, so that we understand that there is more value of the aerosols, optical aerosols, other than the anthropogenic aerosol during the sea breeze onset. So these things we have focused on this part actually, and this is how the figure shows that, and the same thing I'm showing. And the main part of this presentation is about how you can study the fumigation effect in respect to the boundary layer. And these are we have compared with of course, we have done with the minimum gradient of the aerosol extinction coefficient has been taken as the atmospheric boundary layer height from the LIDAR. And then these we compared with the radar sonde profiles, and we found that there is a reasonable match between these two. And then we have proceeded with you can see that this ABL height from the, you can say that mini micropulse LIDAR. And of course, these are the different things which I am not focusing here. And then we also compared this data with the ECMWF boundary layer data. And the interesting thing here is, which I am coming for last slide, this is the important thing I would like to show. Yeah, this is how in season wise what is happening. Just when it comes to the sunrise time, we have calculated sunrise time, and at what time the BC is happening, BC peak is happening, that we have studied. And we have seen that especially in the winter and the summer season, there is no much difference. But when you see in southwest monsoon season and northeast monsoon, you have almost more than 1 hour difference they are taking. It is taking to get the BC peak or the study region. So this shows that, you can see that how this fumigation of aerosols are having the seasonal variations. So we feel that basically that this fumigation of aerosol it will happen daily in the morning, but there is a lot of difference when it happens to the sunrise, and to get the peak in the BC, the time is varying. I think this is how we can understand that fumigation of the aerosols. So with this, we also did some scavenging studies. we have compared with the, you can see that theoretical, you can see that cloud microphysics model we have taken, and through cloud microphysics model we have calculated the angstrom exponent, and here we have used the distillatometer data, and then we compared with the, since we have the BC, we have taken the number of events where the rain is happening. Before the rain, what is the BC, and after the rain, what is the BC, and then we calculated some scavenging ratio from these values. And of course, we have compared the theoretical, scavenging ratio obtained from the cloud microphysics models. So when you see that, there is a good correlation between this relation between BC scavenging ratio and the scavenging ratio coefficient over the study region, which shows that, the cloud microphysics model and, the estimates which we have done with the BC model, they are in good agreement. So with this, I thank you very much for your kind time. Sorry, because of lack of time, I had to run my slides. I apologize for this. Thank you very much.
No, thank you very much, Lakshmi. It was nice, both your presentation about simulation and scavenging. I will take the one question from Nino Alfonso, and he or she say that is it okay because he is studying PM10 estimation using AOD, Moody's MCD 1982. So if you read the chat, he's asking that his question whether
let me read, sir.
So please comment in chat.
Is it acceptable to use data from different satellite products for AOD corrections? Yeah, exactly. As I told that in the beginning, it depends on the data availability. Actually, people started using comparison of, they are trying to understand the discrepancies with the in situ data sets basically. Okay, when it comes to the large scale, what will happen is you will not have sufficient network for the in situ stations. Like, when you take the AeroNet, which is having a wide range of network, even then when you take global scale, these are very, very limited. So we also did that study, but we did not come with some fruitful results actually when you compare with the AeroNet stations basically. So we thought that it is okay, let us go with only satellite products. But of course, we have used 2 to 3 satellites, like when you see that Moody's and MISR and AXR SU. Even as I told that when you take the Moody's and what is that AXR and MISR, for certain wavelengths you don't have any wavelength. Let us suppose we have 440 and 550 wavelengths which are having the Moody's, but the same wavelengths are there for MISR and AXR. So what we have done is we have interpolated the values to the additional, other wavelengths, and then we have used the study. Of course, there are limitations. I agree for that. But when it comes to a small region and local scale, you have in situ measurements. So that is the best I can say that. But when you want to compare globally, there is no other go as of now, what is based on my knowledge, except AeroNet network, which is not sufficient. I feel that. I hope I answered your point.
For more detail, you can interact with Lakshmi. His number, his email is this one. Thank you very much for very useful talks for all the speakers of this session. In fact, we had a very vibrant session, and some queries were there. I thank all the audience who have shown very active involvement by asking questions, and some of the queries are answered. Some queries definitely require a lot of time to interact, and if possible, please interact the speakers by email. And I thank Professor IP for his introductory remarks, because my co-chair has some work and he has gone there. So I have to summarize this session. Has been very fruitful in the sense that new findings were presented. Some of the gaps were also highlighted in this aerosol and remote sensing measurements, and also the importance of satellite data was also highlighted. So with this kind of summary, I would like to close the session, and